Without the addition of any other substances, two water molecules can interact with each other to produce a hydronium ion and a hydroxide ion by transfer of a proton from one water molecule to another. This process is called autoionization.
Water actually has acid and base in it at the same time. If you're drinking water, don't spit your water out, okay? It's good for you. It's totally normal. But anyway, water has what they call autoionization. Those strong hydrogen bonds in there are able to rip a hydrogen ion from one of the waters, making a hydronium and making then a hydroxide in the same place. Now, in normal water, you normally have just as much hydronium as you have hydroxide, and we're going to see it's not a lot, all right? But this is a process that occurs. Water can act as both an acid and a base, and this is only possible through this autoionization process. It's those strong hydrogen bonds, again, creating a really unique effect in water, which is really cool. People have studied this reaction quite a bit, and up there on the top under autoionization, you've got two water molecules in equilibrium with hydroxide and hydronium. Remember, hydroxide is the active part of a base, and hydronium is the active part of an acid. So people have studied this reaction. Now remember, you don't include liquids and solids in equilibrium. So Kw is a type of equilibrium constant expression, and just like all equilibriums, it's products over reactants. We would have the hydronium ion times the hydroxide ion in the top part, but in the bottom part, because water as a liquid is the only playing species in which you don't put in K expressions, you would just have divided by 1. So Kw equals hydronium times hydroxide. At 25 degrees Celsius, Kw has been measured to be 1.00 times 10 to the minus 14th. And that's really less than 1. All right, this is a very reactant-favored reaction. And what that tells you right now, I'm hoping that you're seeing, is that, wow, there's not a lot of hydronium and hydroxide in normal water. All right, it's going to be a really small part. Most of the chemicals in this reaction are going to be liquid water. All right, you only have a very small amount of hydroxide and hydronium running around. In a neutral solution, you should have then just as much hydronium as you have hydroxide. And we want to drink neutral water, right? We don't want to drink water with an excess of acid or an excess of base. So if hydronium and hydroxide are equal, then Kw, which equals hydronium times hydroxide, is basically equal to hydronium squared or hydroxide squared, because it's going to be the same thing in a neutral solution. So if that's the same, Kw, that 1.00 times 10 to the minus 14th, equals essentially x squared. So you can solve for x, the concentration of hydronium or hydroxide, 1.00 times 10 to the minus 7th moles per liter. Now, let's think about that number. That's the amount of acid and the amount of base in normal water at 25 degrees Celsius. And if you've watched the concentrations that we've used in the labs, and we've talked about, a 10 to the minus 7th moles per liter is very small, all right? That's not a lot of acid and base. And this is an amount of acid and base which our bodies are used to. We can accept a 10 to the minus 7th moles per liter acid or base without harm to our bodies. All right, it won't burn on the way down or anything like that. So this hopefully makes you feel good then about drinking water, which you should do anyway. It's a very small amount. Now, believe it or not, of all Chem 223, this 1.00 times 10 to the minus 14th number is going to be super important. A lot of the equations we're going to talk about are based on Kw, so you really need to know / memorize this number. But I also want to put a warning in. In future lectures, I'm just going to start going crazy here with Kw. You'll see all this stuff we're going to do. It's fantastic. But officially, Kw is only effective at 25 25 degrees Celsius. And K, like all equilibrium constants, is temperature dependent. If you're doing acid and base studies in like a human being in the body, the normal body is about 37-ish degrees Celsius. It's warmer than 25 degrees Celsius. And some of the acid-base expressions we're going to talk about may need to be altered a little bit to adjust for the new temperature, because K will change with temperature, and in the body, some of the things we'll talk about may not be quite as accurate. However, overall, most things are done at 25 degrees Celsius, and everything we'll talk about will be pretty effective. But I just want to know, if you're doing medical research, you may want to reconsider some of the things we're going to talk about for your system. You would get a different value of kW and go from there. It's kind of an interesting thing. But most acid-base reactions are done at room temperature, which makes this all really effective. So here's a solution. A solution has a hydronium of 1.0 times 10 to the minus 8th moles per liter. And the question is, what is the hydroxide ion equal to? Good question. All right. This is the first time now that Kw is going to be helpful, because Kw equals hydronium times hydroxide. And we've got the hydronium value there. And if you know what Kw is, and that's a pretty sloppy W, I apologize. But anyway, that Kw is the 1.00 times 10 to the minus 14th. So to solve this problem, you want to solve for hydroxide. Kw, 1.00 10 to the minus 14th, divided by 1.0 times 10 to the minus 8th. That's going to be the way to find hydroxide. If you do that in your calculator, that comes out to be 1.0 times 10 to the minus 6. So this is the kind of thing that you can use Kw for, and there's lots of uses for this, but you do need to know the 1.0 times 10 to the minus 14th number. Cool for school. So calculating the amount of acid and base, i.e. calculating the hydronium hydroxide, is going to be really important. This is the kind of question you might run into. Let's say that you add 0.0010 moles of sodium hydroxide to a liter of pure water. We can use this information to calculate the hydronium and the hydroxide. So what we'll do to figure this problem out is we'll go back to the equilibria with Kw. And remember, that was 2 waters as liquid in equilibrium with hydronium and hydroxide, and Kw was equal to hydronium times hydroxide, etc., etc. We can use Le Chatelier's principle here to do some kind of predictive natures as to how these questions are going to turn out. If we add sodium hydroxide, honestly, we don't care about this sodium. We want to know what's going to happen as we add hydroxide. Well, if you add hydroxide to this equilibrium, which is what this is, hydroxide, a product, we're adding a product, it's going to shift this reaction to the left, all right? Remember, as you add something, in Le Chatelier's principle, it tends to move to the opposite side. We're adding a product, this should make the equilibrium move more towards the reactant side. So the hydronium concentration will go down as we add a base. And that kind of makes sense intuitively, right? Because hydroxide is a base, bases and acids are like cats and dogs, they're really reactive. You add hydroxide, your hydronium should go down. Hydronium will be less than 10 to the minus 7th moles per liter at equilibrium. Hydronium and hydroxide equal 10 to the minus 7 when they're by themselves. But if you add hydroxide, it's going to shift it to the left. Your hydronium concentration should be less than 10 to the minus 7th. So what we can do here is set up another ICE table, all right? ICE again stands for initial change in equilibrium. We don't need the water because liquids and solids are exempt from equilibria, but of course we do need hydronium and hydroxide. So the way I would do this is to think about the hydroxide as initially we've got 0.0010 moles per liter going in, and the hydronium initially is 0. Now, in the Kw expression, hydronium and hydroxide will be non-zero numbers, and as the water breaks down, it will make X amount of hydronium and X amount of hydroxide. So at equilibrium, hydronium will be X, hydroxide 0.0010 0.0 plus x. And knowing those values at equilibrium, we can set them equal to kW, 1.00 times 10 to the minus 14th. So kW equals x times, parentheses, 0.0010 plus x. In an equation like this one right here, all right, if we were going to set this up, you could write this out, and it would be x times both of the pieces inside, which would be x squared plus 0.0010x, and you could put kW on the other side, and this would be a quadratic formula. All right, you'd have x squared term, you'd have an x term, the number would be the kW, all right, and there's nothing wrong with solving it that way. However, you can also use common sense a little bit to make your life a lot easier. Now remember, before the hydroxide was added to the water, X, the hydronium and hydroxide, was 10 to the minus 7. 10 to the minus 3, which is what 0.0010 is. 10 to the minus 3 plus 10 to the minus 7th, which is what you would have had under pure water. The 10 to the minus 3 is so much bigger than the 10 to the minus 7, you can basically ignore it. Like mathematically, put 0.0010 plus 10 to the minus 7th. And to any kind of sig figs, especially the ones we're dealing with here, the answer will be 0.0010. It's like if you had, say, 1,000 pieces and you added one more. It's probably not going to make a big difference if you have 1,001, maybe if it was a gold bar or something, but normally having an extra piece with that many, it's not a big deal, all right? In science, believe it or not, significant figures can be your friend. So instead of having a quadratic formula, which you could solve for, you can actually just say, hey, this little plus x here, it's going to be pretty small. And if it is pretty small, it makes your life a lot easier, because instead of having an x squared and a 0.001x, you can cross that part out, and kW equals 0.0010 times x. So if you do that, your life is a heck of a lot easier. Instead of having a quadratic, you can abbreviate it as kW equals x times 0.0010. Now remember, x is hydronium here, so let's put hydronium back in. kW divided by 0.0010 will be your hydronium. 1.0 times 10 to the minus 11th is the answer. Now, if you're feeling weird about making these kind of assumptions, you can always take the answer here, 10 to the minus 11th, and put it back up here. Does it make a big difference on the hydroxide? We were talking about 0.0010 plus a 10 to the minus 7th number. The number we calculated is even smaller. It's 1.0 times 10 to the minus 11th. And 0.0010, a 10 to the minus 3 number, plus a 10 to the minus 11th, it's going to be like, 100 million plus 1. It doesn't make any difference. That extra 1 is not a big deal. With sig figs here, we're limited to the 10th, 100th, and we're limited to the 0.0010 position right there. All right, that would be the 10,000th position. And that's where we have to cut the sig figs off. And a 10 to the minus 11 plus that number is still going to be 0.0010. So for all of these reasons, I do recommend starting to think about when you can cut out little x, because you don't have to go to quadratics or anything like that. And even if you use the cool solve function on your calculators, which I did encourage in the last section, it's going to take you longer to put in those numbers in your calculator to hit solve than if you do it this way. And you're going to get the same result almost all the time. So this is something we'll start talking about when you can sometimes pull out a plus x. And if you do, it makes your life easier. I am the lazy chemist, but all I'm trying to do here is save you some time. When you have 0.0010 mole of sodium hydroxide, the hydronium goes from 10 to the minus 7th in neutral water to 10 to the minus 11th moles per liter. And of course, that's pretty small. This solution would be considered basic, all right? Your hydronium, 10 to the minus 11th, is so much smaller than the 10 to the minus 3 moles per liter hydroxide. And anytime you have more hydroxide than hydronium, we would consider this number to be basic. If the hydronium value was larger than hydroxide, that's when we would consider it to be acidic. But in this case, more base than acid, this is going to be basic. Now, using 10 to the minus whatever numbers is kind of unwieldy sometimes. So instead of using that, we use the pH scale. And pH is just a more common sense kind of number, which you can then figure out quickly if something is acidic or basic. The pH scale supposedly was developed by Sorensen. Again, another cool person with the O's with the lines through the middle of it. The P stands for potential, supposedly. So pH is the potential of the hydrogen ion to do things. Anyway, pH is equal to minus log of the hydronium concentration. So the number you calculated in the last slide, you could plug this into pH expression to see what the pH is. Now, in a neutral solution, like we saw earlier, hydronium and hydroxide are both equal to 10 to the minus 7th moles per liter at room temperature. So the way that people get the pH of a neutral solution minus log of that number, pH equals 7. So pH will equal 7 for neutral solutions. But realize now that in a neutral solution, it's not that you don't have any acid and base, it's just that the amount of acid equals the amount of base. And they're really small amounts, so they don't really interact with each other. However, there is both acid and base in there, and that's something kind of interesting. So if I said you had a pH of 7, you'll know instantly that it's neutral now, because pH of 7 is the neutrality point in pH. On the other hand, if I said, well, I had a hydronium of 1.00 times 10 to the minus 7th, it's going to take a little bit longer to process what that means and to think about if it's acidic or basic. So this is just one kind of cool technique that scientists use. The pH scale, super helpful for instantly telling if something is acidic or basic or neutral. The 0.0010 molar sodium hydroxide solution, we can calculate the pH, and what the heck, let's do that. We saw the hydronium was a 10 to the minus 11th number, so pH minus log of 1.0 times 10 to the minus 11th, this pH comes out to be 11, all right, 11.00. And again, pHs that are larger than 7 are the ones that are going to be basic. So basic solutions, first of all, will have a pH larger than 7. And having a basic solution just means that the hydroxide, this number, is larger than the hydronium, this number. You have more hydroxide than you have hydronium. An acidic solution, you'd have the reverse case. In an acidic solution, you'd have more hydronium than you have hydroxide, and your pH values will be less than 7. And then neutrality just means that your pH is equal to 7. The acid and base quantities are equal. Depending on the situation, sometimes pHs can be about 7 to be considered neutral. It kind of is in a case-by-case basis, but realize that pure 7 would be the pure neutrality point, and you can go from there. If you have a solution with a pH of 10.5, how would we describe it? And the answers are acidic, basic, neutral, and lame. Lame could be the answer, I won't deny it, but let's try and keep our science hats on here for a little bit. The pH number will tell you which one it is, and of course, pH is larger than 7, those are going to be considered basic. All right, so quickly you can tell if something is acidic, basic, or neutral. Acidic would be numbers less than 7, neutral would be equal to 7, or very, very, very close to 7, etc., etc. And they still could be lame, but that's not really where we're talking about now. Oh well. You can find the pH of a lot of things around you. I used to drink a lot of Diet Coke. You can put a pH probe, which is what that thing is there in the lower right corner. You can put a pH probe in Diet Coke or beer or wine or water or anything you want to and stuff, and you'll get the pH. pH probes are pretty cool. If we're doing face-to-face labs, we'll use a pH probe to find the pH of a solution. But anyway, you put the pH probe in your Diet Coke, the pH comes out to be 3.12. Well, in this case, then, your Diet Coke would be considered acidic because the pH is less than 7. That means more hydronium relative to hydroxide. Most of the things we eat and drink are somewhat acidic. How much acid is there, Dr. Russell? Great questions, random student in the back of the room. Let's figure it out. So pH equals minus log of the hydronium. So if you want to know how much hydronium, how much acid, moles per liter there would be, let's deconstruct that 3.12. We'll put 3.12 in for pH and we'll solve for hydronium. Now, this is a base 10 log, log, and it's super important that you use base 10 log and not the natural log, ln. You'll get different numbers here, so make sure that your logarithm is log. And I highly encourage you to go through some of these examples to make sure that you're getting these numbers. So log of hydronium equals minus pH if you put the negative on the other side. The anti-log is the way to get rid of that log. And the anti-log for a base 10 log, it's 10 to the x. This is just math fun, and you don't have to be an expert in logarithms to make this happen. But on your calculator, there's often an log button, and then second function log on your calculator, it usually has a little 10 to the x. That's the anti-log, all right? So if you wanted to find the amount of hydronium, you would take the anti-log of both sides. Hydronium equals 10 to the minus pH. So it's like 10 raised to the power of log hydronium equals 10 raised to the power of minus pH. The 10 and the base 10 logs cancel out, so that's where hydronium comes from. And then on the other side, you have 10 raised to the power of minus pH. Now, anti-logs are pretty chill. 10 little caret if you want, minus 3.12, or if you have the number, you can do it. You should get 7.6 times 10 to the minus 4 moles per liter. So when I used to drink Diet Coke, then I would be drinking a 7.6 times 10 to the minus 4 molar acidic solution. Oh, joy. A solution has a pH of 4.50. The hydronium concentration is, and you can figure it out. Okay, so this is going just like in the last example from a pH to a hydronium. As we saw, hydronium is 10 raised to the power of negative 4.50. So again, this is something to do in your calculators. And if you do that, it comes out to be answer B, 3.2 times 10 to the minus 5. So this is how you can figure out hydroniums from pH. And again, if you went minus log 3.2 times 10 to the minus 5, you should get an answer of 4.50. If you are a person that's interested in significant figures, some of the numbers I've used recently maybe haven't made a lot of sense. So I want to talk here about how to figure out significant figures from logarithms. And I'm going to try in Chem 223 to be a little bit mellow when it comes to sig figs. In earlier classes, I was tenacious and I was always after you for doing sig figs. Logarithms are a little bit weird. I recognize it, but I also want you to understand where the numbers come from. I'd like you to have an approximate appreciation for how to do this. The more, of course, you follow it, the better and stuff and see. So when it comes to significant figures and logarithms, all right, logarithms are really just exponents with special significant figure rules applied. And in general, the log of an experimentally measured number with n sig figs gives numbers with n decimal places after the decimal, all right? So this is a little bit weird, but let's say you're taking a number with a molarity of 3.2 times 10 to the minus 4. Well, 3.2 means that would be 2 sig figs. That's the n would be 2. And if you're going to take the log of that number, you might get, who knows what kind of number, but your reported value should have 2 numbers past the decimal point, all right? That's what it means when it says n decimal places after the decimal. So if you have 2 sig figs, you would have something point something something and the something something after the dot, that would show you number of sig figs. Now if that's as clear as mud, I apologize. Let's look at some examples. The first one here, log 3.07 times 10 to the minus 3. So this is a 3 sig fig number, 3.07. We don't include the exponents. So the answer here, we would have 3 sig figs past the decimal, all right, 3 numbers past the decimal. The 2 there is somehow all related to the power of 10, the 10 to the minus 3. That's the way I think about it, all right? So 3 sig figs in means 3 sig figs past the decimal. Log of 1.1 times 10 to the minus 8th, that's a 2 sig fig number again. So we would have 2 digits past the decimal. So that would be 7.96. Now look, it looks like you're going from 2 sig figs to 3 sig figs, 7.96. But in these logarithms world, the 7 just tells you the power of 10 to use. So scientists then don't look at that number for sig figs. We would look at the 0.96. And this definitely becomes important if you do an anti-log, an anti-natural log, or an anti-base 10 log. 10 raised to the power of negative 3.12. This is the anti-logarithm function. And so in this case, we want to convert this number, this pH-like number, back to a regular. 2 numbers past the decimal means 2 sig figs in the final answer. So this gets a little strange, but you can see here we went from what looks like a 3 sig fig to a 2 sig fig. But again, the only digits that count are the numbers past the decimal when you're dealing with logarithms. All right. So this is a little bit weird. I totally understand, but that's going to be the basis for a lot of the calculations you're going to see in these sections. And again, if you have questions on this, let me know. Try to use reasonable significant figures in your answers. If you use these rules, that's of course the best, all right? But they can be a little bit weird. Just try not to go crazy on me on sig figs, all right? The substances around us definitely have pH values, and again, most of the time the things we eat and drink are somewhat acidic, and the things that we use for cleaners oftentimes are basic. Blood is kind of in the middle. Blood pH changes a little bit, but you can see it's usually a little bit basic, and that's kind of cool. So quickly, by seeing those numbers like pH of 3.8 for the orange, you know that that's acidic. On the other hand, pH of 11 for ammonia, that would be very basic. Don't be trying to eat and drink basic things by default. Our bodies are more set up for acidic things than basic things. Sorensen, when he developed the pH scale, it was actually kind of a broader thing than just pH. You can have a px scale for any quantity x. So px equals minus log of x. So the potential of the x ion equals minus log of the concentration of the x ion. It's kind of cool, and we're going to use this. pKa is something we'll use here coming up, and I haven't talked about Ka yet, but I do want you to see that pKa equals minus log of Ka. So instead of this x, we're putting Ka in. I'll talk about what Ka is here a little bit, but just realize pKa equals minus log of the Ka. POH is another thing we're going to talk about soon. POH equals minus log of the hydroxide ion. So if you have so much hydroxide ion, minus log of that number will give you the POH scale. Kw equals hydronium times hydroxide, and it equals 1.00 times 10 to the minus 14th at that almost magical room temperature 25 degrees Celsius. There's some interesting things you can do with this expression right here. Minus log of hydronium is pH, minus log of hydroxide is POH. In the world of logarithms, if you go minus log hydronium times hydroxide, you can actually break that up. You can break up minus log hydronium times hydroxide into minus log hydronium plus minus log of hydroxide. This is a reason why people like using logarithms in science. And that equals then minus log of Kw minus log of 10 to the minus 14th. Minus log of 10 to the minus 14th is just 14, and minus log of hydronium is pH, and minus log of hydroxide is POH. Lo and behold, 14 equals pH plus POH is going to be something pretty important. If you have pH, you can quickly find POH. If you have POH, you can quickly find pH. It comes from the Kw expression, equals hydronium times hydroxide, but sometimes it's more helpful to think about it in pH versus POH than hydronium and hydroxide. That weird pKa thing up there that I mentioned, there's also a pKb, and you can probably imagine that the big K isn't equal equilibrium constant, yes. And the little a and the little b stands for acid and base, also yes. When we talk about pKa and Ka and pKb and Kb, we're going to see that 14 equals pKa plus pKb. And we'll talk about that later, so just hang on. But for right now, what I want you to see is 14 equals pH plus pOH. Again, that's for room temperature. If you do other temperatures, it may not be equal to 14, it'd be somewhat different. Also realize that there is a PKA Kickboxing Association, Professional Kickboxers of America, something like that, but that's different than the PKA we're going to talk about. Sorry about that. A solution has a hydronium ion concentration of 3.2 times 10 to the minus 5 moles per liter. What is the pOH? Okay, so there's a couple different ways that you can do this problem, all right? So hydronium is the H3O plus, and we want to somehow get a pOH out of it. And so one way to do this would be to use Kw. Kw equals hydronium, that number, times hydroxide. You could solve for hydroxide, and then minus log of hydroxide would give you the pOH. Another way to do this is you could figure out pH of the hydronium. pH equals minus log 3.2 times 10 to the minus 5. And then whatever pH is, 14 minus pH would give you pOH. So either way you do this is fine. In this problem, it looks like what I did was something totally different. pOH equals minus log of hydroxide, and hydroxide is Kw divided by hydronium. So I plugged all those pieces in there to get 9.51. All of these ways are fine, and you pick the one which works best for you. That's what's really important. As long as you can get the 9.51 answer, I'm very, very pleased. Litmus paper is a way in a chemistry lab that you can quickly tell if something is acidic or basic. And there's different kinds of litmus paper, but these litmus papers here turn a little bit more reddish orange, or I guess it's more orange color if it's acidic, and a little bit more blue or that dark purple there if it's basic. And the amount of acid and base will make a big difference. Now, in this lecture so far, we've talked about pH and hydronium, and we've also made some connections with pOH and hydroxide. And we're going to use all four of these quite a bit here. So let's talk about pH first. We saw that pH usually goes from 0 to 14 and neutrality is 7. And that comes from the fact that hydronium and hydroxide are both equal to 10 to the minus 7 if it's neutral. But in a basic solution, you're going to have more hydroxide than you would have hydronium. And in an acidic solution, you'd have more acid than you would have base. So in an acidic solution, your pHs will be closer to 0, definitely greater than 7, closer to 0, depending on how much acid there are. And the concentration of the moles per liter, if you will, of hydronium will be a number which approaches 1. All right, I have moles per liter of 1 mole per liter would be a pH of 0. So it'll be some number between 10 to the minus 7 and 1. Now, as hydronium goes up, hydroxide goes down. Kw equals hydronium times hydroxide. So if you have a hydronium of 1, your hydroxide is going to be very small. So notice that as the acid amount is getting bigger, the base amount is getting smaller, all right? As hydronium goes from 10 to the minus 14 to 1, the hydroxide goes from 1 to 10 to the minus 14. What this means is that as hydronium goes up, the hydroxide goes down, because both of those together must equal Kw. But here's where it gets a little weird. As the acid goes up, the pH goes down. It goes from 14 basic to 0 acidic. So hydronium goes up and pH goes down. On the other hand, pOH, which is a reflection of base here, pOH is going to get bigger as the acid gets bigger too, all right? The hydroxide is decreasing as the acid goes up, so that means the pOH is increasing. So what I want you to do in this slide is just take a minute and think about these relationships, all right? Because in an acidic solution, you're going to have a low pH, because pH will go to 0 as it gets acidic. And in an acidic solution, that means you have a high amount of hydronium. But high amount of hydronium means low amount of hydroxide. Hydronium times hydroxide, remember, equals Kw. Low amount of hydroxide, high pOH. So notice this back and forth kind of thing. So again, acidic solutions, low pH but high hydronium. High hydronium means low hydroxide. Low hydroxide means high pOH. Think about this in your mind. Get this clear. It makes your life a lot easier. In basic solutions, it's the opposite. In a basic solution, you would have a high pH. It would be larger than 7. And basic solutions means your hydroxide will be higher. That means your hydronium will be lower. But high hydroxide, small pOH. pOH is going to be smaller. Just like acidic solutions have small pHs, basic solutions have small pOHs. So this up-down kind of thing is something you really got to get clear in your head to figure this out. It's not hard. Just kind of go through it. You can always put in random numbers. So like put in a pH of 3 and figure out what hydronium, hydroxide, and pOH is. You can do the same thing with basic solutions. Put in a pH of 10 or something. Figure out what hydronium, hydroxide, pOH. You can see it that way too.